So, this is a 20-minute talk I have yet to give in less than an hour. I'll see what I can do. How many slides? It's only 20 slides. It should be 20 minutes. Okay, so what's the motivation behind reducers? It is performance. And it achieves performance in a couple of ways, but a point I want to make right up front is it's not about, ooh, can we eke out a little bit more of whatever? I don't really believe in that kind of performance tuning. I mean, if it's something big, that matters, but little tiny, ooh, it's now 10% faster, is not what this is about. This is about programs recovering a property they had 10 years ago, right? 10 years ago, if you wanted to make your program faster, what'd you do? You waited 18 months, and a new computer came out, and your program was twice as fast. The same program that you didn't touch was twice as fast, right? This is a property that we've lost, and we've lost it because clock speeds have topped out, right? A sequential program gets faster when you get a new computer that has a faster clock speed. If your new computers never have a substantially faster clock speed, you lose this property. Now, 10 years ago, if you had a bunch of software and you hated your old computer and you bought a new computer and none of your software got faster, you would have been pissed, right? You would have been very upset. And that will start to happen again today. People are sort of like, wow, this new computer is not that much faster than my old computer. But people running racks of computers with dozens of cores in them will start to be pissed again if the software you've given them does not get faster merely by them buying a new computer. And so I think it's imperative for programming languages to attain the property once again that a new computer makes the program faster. And a new computer is only going to have more cores. That's going to be the only way our programs get faster. So the key motivation here is to restore the property to closure that all programs used to have, which is that when you get new hardware, it gets faster. So we see two performance paths in the reducers. One is we just do less allocation than lazy seeks in the case where you are going to consume the entire seek and if it's in memory, as was just said. But also the bigger gains and the ones that propagate across new computers are the ones from parallelism. So this really matters. I don't care if you think Clojure is fast enough. Clojure will not be fast enough for you if your boss says, I'm tired of using this language that doesn't get faster when I get a new computer. So the inspirations for this, positively and negatively, are the Haskell iteratees and the Sky Steel talk. I'm not going to have enough time today to dig into the differences between reducers and these things, but they are different and they're different in significant ways. But those are two sources you could go and look at. So how did we get where we are? We got where we are because of the history of functional programming. Functional programming was born in languages that only had lists as data structures and of a mathematical bent for analyzing computation that favored recursion. Right, so there's this whole, you make this base case and then you have the recursive case and you're going to define everything that way. It's pretty. It's certainly pretty. And using lists or sequences to do this is really great. Clojure, when I first built it, did not innovate in this area at all in terms of adopting this model of computation. It adopted this model of computation. The only thing that I did was sort of try to abstract seeks away from the concrete representations they had in con cells. But the important point, and the point really that's made by the Guy Steele talk, is this is inherently sequential. There's no way to break away from the inherent sequentiality of using lists and sequences. They're stuck there. Their semantics are sequential in a way that can't be broken. In fact, that vector example, it will never happen because you can't map a function on a vector and then lazy realize the items by random access, because that breaks the sequential promise of map, which is that if you have any side effects associated with the function you're mapping, they will happen in order once per item. So you can't walk away from the sequentiality nature of that any too easily, certainly not as easily as that slide showed. So where are we going? We're going to get more cores. We have to get the speed from that, and we have to have a new model. So let's look at our models. The old model, for computation was just loops, right? You set up an accumulator, this is before we had higher level programming languages, assembly language. You make an accumulator, you write this loop, you go to there, you bang on that thing, you build up a result. And then we moved up from that to, really what we see in functional programming now. Functions on lists, higher order functions on collections. What's nice about seekable as a concept is it really sort of turns all those sequence functions into functions of collections instead of functions of, precisely sequences. And you start actually not to have to care a lot about answering the question whether or not something is a sequence. But the future, as we move forward, is more collection independence still. And if we ever want to achieve parallelism, we have to get order independence. We have to break away from these two things. So if we look at the inside of a typical sequence function, like map, we see that it does a lot, right? This isn't the precise definition of closures map, but it's the classical definition, right? You're mapping a function across a collection. That implies, consing, applying the function to the first item of the collection, to recursively mapping that function on the rest of the collection. This is the logical model for what map does. And look how much is in here. There's recursion, right? There's definitely an order promise and presumption. So promise, I will execute the function on the first thing and then on the rest, and because that's recursive, I'll do it on the first thing of the rest and the next thing of the rest, and so forth. So there's order in there. In closure, it's not actually cons, it's lazy cons, so we add a laziness promise. It consumes a list. Now, of course, we know we can get to that list notion from a number of things, strings and vectors and maps, and we have a path to this. But the code we're writing is still saying, I consume a sequence and produce a sequence. Right? It both consumes a list and builds a list. So it's doing too much. I didn't even put what it does. What does it do? It's not any one of these things. That's really interesting, right? I just list 5 things that map does, none of which are the core of what map does. That's a problem. So how can we do better? Well, one of the things that may or may not be known to everyone now is how many people know that reduce now lets the collection drive if that's possible? Wow. This is my secret. You already have this. This is in 1.4. So the classical model of reduce was take an element, take the first element of the seek, that is this thing, and combine it with the initial value using a binary operator, and take the result of that and do it the next. And it was a loop recur, which is pretty peppy. It does process the entire list. But there's actually nothing in the definition of reduce as a piece of semantics that required it to operate that way. I mean, it doesn't actually need to make a seek out of the thing. It just needs to make sure that the elements of the thing are combined one at a time using this combining function, using this binary reducing function. So it's really, so now we have a protocol that says, if you know how to collection, you reduce yourself. Like, I'm not even going to do this. I'm not going to turn you into a seek. I'm not going to write a loop, right? Unless you don't know how to do it yourself, in which case it does fall back to that old definition. But there's a path now to letting the collection, or somebody else who's built this protocol extension, to say, this is how this collection reduces. So, so you can become ignorant of collection structure by doing this. The other thing we know about reduce is it can build anything, right? Reduce is sort of process the entire thing and produce anything. So we can reduce with plus and get a number out, or we can reduce with, with Soch and get a map out, right? Reduce can build anything. So reduce now is independent of the input collection and can build anything. Those are both great. We've also sucked something else out of this, which is laziness. Reduce has never been lazy, so now it doesn't make the laziness problem. So now we had those 5 things that we didn't really do before, 3 of which we don't do anymore, right? Reduce does not have a laziness presumption. It does not have a presumption of the shape of the input or the shape of the result. It's big. They're gone. But it still is inherently sequential in its semantics, right? It doesn't require a sequential structure. It doesn't require you meet it at a sequential structure on the input side, but it does have sequential semantics in the application order, right? It is going to take the first element and the initial value and combine them, and then the next one and the result of that, and so on and so forth. So effectively, it's still a left fold with a seed. But as a path to trying to make, so the objective is we're trying to make map, if we want to reach parallelism, we have to break away from sequentiality. And if we want to break away from sequentiality, we can't define everything in terms of let's meet at sequence. So the first tool we need to do is to make map and those other functions collection ignorant. And so one idea is build them on reduce. If we can build them on reduce, we get that collection ignorant property of reduce for free. And so what we want to do is we want to use reduce, and while reduce has an ordering promise, you can always ignore that, right? In other words, the logical notion of mapping a function on a collection, does it have an order promise? No. If I say map ink across this collection, what I really care about is what was envisioned on the slide before. If I had a vector, I might want a vector with everything, every number one bigger than that. Because map and filter actually don't have ordering promises inherently in the semantics of the key operation, the one I left off the slide. Map means this collection with this function applied to all of its members, or this collection with some of its members removed due to filtering. So we want to use reduce. We want to ignore its ordering promise. Right? If we can just ignore it, in other words, not rely upon it, not write any code that cares about it, we become stronger in our isolation from that promise, because we don't need to. And then the trick is, what do we want to build? And the answer is nothing. Right? The approach that's taken in this design is to say, we want to build on reduce, and we want to build upon reduce, but we don't want to build any concrete result necessarily. So what are we going to do? Right? We're going to call reduce is eventually going to be called, and we run a map, and map itself is not going to do the work. We want to sort of delay that, and the way that's going to happen is what I've been calling these reduction transformers. Right? We're not going to make a new collection right when we call map or filter. What we're going to do is take that collection and change what reduce means for that collection, right, by modifying the reducing function. This actually is no easier when I say it than when I wrote it down. It probably isn't much easier to hear. So I have this analogy I've been using in these talks, which seems to work, which is the pie maker. So there's a guy who makes pies. He's an expert pie maker. And he makes pies out of a bag of apples. And he has an assistant, right, who's in charge of handing him the apples when he makes the pie. And a reducing transformer is like telling the assistant to do something when they hand the apples to the pie maker. So mapping is telling the assistant, take the stickers off every apple. Map, take the stickers off the apples. Now, the guy could go and say, I'm going to take the stickers off all the apples and put them in another bag. Or he could just say, all right, I know, before we put them in the pie, I have to take the stickers off. You could also tell the assistant, remove the rotten apples, or filter out the good apples. Filter for good apples. And he would be like, okay, so all the apples are going to have stickers, I'm going to take them off. They say organic, take them off. And then I'm going to look at the apple and see if it's any good. And if it's not good, I'm just not going to hand it to the pie maker. And so what's happened is you built up this recipe for a modified version of that bag of apples that has no stickers on the apples and no rotten apples in it. But that work has not happened. Right? And that seems like lazy seeks, but lazy seeks are actually recipes for much bigger things. They're recipes for sequences of apples that take sequences of apples, not just like logically there's a bag of apples and somehow in the pie making process they won't have stickers or rotten apples. And that's what it means to modify the reducing function. Right? Reducing function is going to be reduce the apples into pie. So what we want to do is try to think about the thing I left off that slide. I said, look at all the stuff that map does. It had everything that map does except for what map does. Right? So what does map do? This is in a context here still. Everybody can see my dot? Right? Let's just try to get the essence of mapping. What does mapping mean? What does it mean to be mapping? And I'm going to say, if you want to map a function, there's a way to think about that that's like this. Imagine you had a reducing function. So we should pause now and talk about what a reducing function is. A reducing function is the function you would pass to reduce. Right? So you can reduce with plus, right? Or you can reduce with conj. We know from those two things that that's a binary operator, right? It's going to take two things and return another. And plus really doesn't distinguish its arguments. But in the context of reduction, the two arguments are not symmetric. Right? The first argument is really what? It's kind of accumulator or result that you're building up. And the second argument is really what? An input to that result. An input to the process that's building that result. And that semantic is a really important semantic of reducing functions. You can't lose track of it. And when you call reduce with the seed, it's very clear because the seed constitutes the initial value of the accumulator or the result that you're going to build up. So imagine here that we've got one of those functions. This is a function of two arguments. This is a function of a result and an input. What we're going to do in mapping is just transform it. We're going to take one of those and we're going to return one. We're going to return a function of a result and input. It's going to go and call the original reducing function with the result, but first it's going to mess with that input. This line, this one thing right here, this is what mapping means. This is all that mapping means. It has nothing, it's connected to nothing else in the universe. Mapping is doing that. Taking stickers, take the sticker off the apple before you make pie. That's what that says. Doesn't know where they came from, doesn't know where they're going. It actually doesn't know what this does. It just knows take the sticker off first. So that's good. I like the essential nature of that. But let's try to lift it up. I think there are two cases that always bother you whenever you're trying to do anything in this area. When you're trying to do anything with sequencing or collection processing or transformation functions or whatever, there's always three cases. One is essentially the mapping case, or what I would call the one-to-one case. There's an operation that happens for everything and has a result for everything. It's effectively mapping, but there are other flavors of it. Right? The other case, the second case, is one where you're going to get every input, but you may not utilize it. Filter is an example of that, right? And I want to filter stuff out. So let's look at filtering from the same perspective. Filtering takes a predicate, right? We know that's part of the essence of filtering. And we're going to define filtering as something that takes a reducing function, returns one, and what does it do? It says if the predicate is true, right, call the reducing function on the result with this new input. But the cool thing here is, what if the predicate's not true? Just don't touch the result. This is the ideal way to write filter. Filter is actually very difficult to write. If you see filters written in a MapReduce context, they have to start wrapping everything in a collection and returning empty collection to mean there was nothing in this spot, right? Because they've been forced to produce a result at every step. Now, what do? You just don't do it. Don't put it in the pie. Just don't put it in the pie. So filtering is really great. It's just the absence of activity. It's not do dummy activity, do separator activity. So that's great. And if you can do this, you can do any kind of process that produces fewer results per input than it got. So that's good. And you can imagine the third case is one in which for every input, you're going to have more than one result. And mapcat is an example of that. Everyone knows what mapcat does, right? It maps a function across a collection, and the presumption of mapcat is that that function itself also returns a collection. And what we want the result of mapcat to be is not a sequence of collections, but one collection. So we want to concatenate all the results together. So here we have mapcat. I hope it's not too low. Mapcatting, right? The essence of mapcatting. Mapcatting takes a function that's going to map across, right, and concatenate the results. It's going to be a function of a reducing function that once you give me a reducing function, you give me make pies, I give you back make pies with, actually this doesn't correspond to make pies. This is, you give me make pies, I give you back make pies without stickers. So now we're going to say same thing. We're going to get a reducing function, return one, and so what do we need to do? We're going to have to call f on the input. That's going to give us a collection. And then somebody said reduce with this other thing, and now you have more than one thing. If somebody says reduce with the function, and I have more than one thing, what function can I use to do that? I could use reduce, right? So if you have more than one result in a reducing function, you can just apply it more than once to the result, and you can do that by calling reduce itself. So this is just going to go and say, I called this and I got n guys out of it. I'm now going to apply the reducing function n times to the result, really, by calling reduce. So having an expansive function means affecting the result more than once before you return it. So we can affect the result every time, that's map. Affect the result only sometimes, that's filtering. Affect the result more than once, that's any kind of expansive process. And because we can do all three of these this way, this reads to me as a general solution. What else is cool is, what's different between these two things? Right, they all share all this gobbledygook. Right, we know this boilerplate is going to disappear. It's going to be the victim of a macro, right? So what is actually left inside each of these? Something I think is really frighteningly pure. It really is the essence of what they do. So that makes me feel good. But if we were to use what I just showed you raw, it's kind of backwards from what we're used to, right? Because this has, we said mapping, right, with some parameter, returns a function that expects a reducing function, and returns one which you can then reduce with. This does not look like fun, right? This is not something we're going to be able to compose or anything else. It doesn't correspond with our model. And our model was this, right? If you try to stay away from the particularities of sequence semantics, right? The model is, you have a collection, you do stuff to it, you get another collection, right? This is what we like to write. We have a whole bunch of code that has this shape, trying to recover that now. One of the things we have to do if we're going to do this is we really have to minimize our notion of what collection means. Because when I tell the assistant to make a bag of apples that has no stickers on it and no rotten apples in it, and he says, yeah, I'll take care of it, and he doesn't actually do anything with the apples, we don't really have another bag of apples yet, right? We don't have a fixed bag of apples. We just have this recipe. But we know what about the recipe? We know we can make pie out of it. Right? We know it's reducible into pie, or it's reducible at all. I can make pie out of it, or I can make applesauce out of it, right? Doesn't matter where I'm going to end up. I know it's reducible, but it may have lost other properties. Like if I ask the assistant how many apples are in that bag, and he's like, oh, geez, I didn't actually do the work yet. I don't know, right? Because I didn't yet take the stickers off and throw the rotten ones out, right? So it can't answer questions like that. It doesn't have indexability or other properties of collections. So we have to really suck collection down to something extremely small. I'm going to say that extremely small thing is reducibility, right? The minimal case now is not seek, it's reducibility. If you're reducible, you're some kind of a collection, right? You have more than one thing in you, potentially, and I can give you a function to do to everything that's in you, and you can do that and give me the answer. That's kind of a collection. Right? It's one property of a collection. So we want something that's reducible. So we can imagine defining a function called reducer. We saw already that reduce asks the thing that's being reduced to do the work first through a protocol. So if we can support that protocol, we can be the assistant who's going to fake that he already did the work of making a new bag of apples, but is just going to do it on the fly. Right? So we want to reify call reduce, which is where that protocol lives, and we're going to implement call reduce. Right? So we're being handed a collection. Now this is the real collection. This is the bag of apples. This is the thing that we made, which is remove the stickers. And what's going to happen is we're just going to ask the collection to reduce itself, modifying whatever it was done. So this is, make pies. We're going to remove stickers and then make pies. And then we're going to ask the collection to reduce itself with that. So all a reducer does is implement the reducible interface by saying, if you ask me to reduce myself, I'm going to ask the collection to reduce itself with the modified reducing function. And therefore, I'm reducible. And that gives us a call like this, reduce plus 0, and then we can make a reducer of this collection mapping increment over it. It's not exactly the shape that we're used to, but it's moved the process to be a function of the collection. Right? Mapping is a function of the collection. The bag of apples without rotten apples and with no stickers on it is a function of the collection as opposed to a function of making pies. So that's an important move there. And then what's left is just to give us the same model. And of course, you notice I didn't call the essence of mapping map yet because I wanted to save it. So I saved it. So there's one other point here. Right? How many times do I need to write reducer? One, I'm done. Does it care what this does? Does it care if it's expansive or contractive or any of the things I just talked about? No. Right? This is done once and for all forever. This will turn any reducing transforming function into a reducer. Any and every one that we ever write. We're done with this. Boilerplate removed. So we can now define map with the signature and result that we're used to. Map some function on a collection will return a reducer of that collection with this essence, with this transformation plugged in. Same thing for filter, same thing for mapcat. They all look the same. So all this stuff is boilerplate. It's all going to be victim of a macro. That means that extending the system or writing any functions that work in the system is about writing the essence of the job and that only, which I think is critically important. All of our functions so far have had 5 other things, had nothing to do with what they do. Now they're gone. And now we get this calling, reduce plus 0, map, inc, 1, 2, 3, 4. We're right back to where we were. This is our model. This is what we like. The only thing that's different is, what are the semantics of what we've returned? It's a minimized semantic for collections that boils down to reducible. So this is great, but reduce itself is still sequential. I didn't fix reduce. I didn't change reduce. Reduce still says, apply this stuff in order, and even when you ask the collection to do it, it has to satisfy the same semantic. Do it in order across all of your contents. And if they have order, that matters, and if the thing has side effects, that matters. So that we can't change this promise, so we're going to need another function. It's still sequential. There are performance gains from this, and I'll show you them in a second. But this is not what it's about, right? So a lot of people have sort of assessed the thing and said, all you're doing is, you know, handmade stream fusion, right? Because they're stopping at reduce. If all we got out of this was reduce, yeah. I mean, I still think it's really neat, because you're defining stuff with their pure essence. But that's not the cake. Right? The cake is fold. Right? All that we have left to take out of this process is the order promise of reduce, and that's exactly what fold does. So we have to have a new function, but I'm claiming this name. Right? Clojure has not used it before. Right? For many languages, this means one of these two specifically. Reduce is the same as foldel. Some languages have fold mean foldel or foldar. I mean something new with fold. It's still in the same category. I mean order-dependent fold. That the semantic promise of fold is it might be run in parallel. Beware. I/O, I don't think so. You know, warning, warning. This is potentially parallel. It's part of the promise, not that it is parallel, but that it might be. Beware. Of course, also be hopeful, right? And the way fold works is with the reduce plus combine strategy. Now, again, I don't have enough time to talk about this, but if you've seen the Guy Steele talk or you go watch the talk, there's going to be a section in the talk where he describes filter. He says we can use fork join to do parallelism, which is true, and that we can use a map reduce strategy to do that, which is also true. But I reject that that's the right way to do it. Because what ends up happening is the fact of fork join is this. You're going to take your work, you're going to divide it up in half. You're going to take those halves and divide them in half. Eventually you're going to get to a point where you're going to do the work sequentially. In other words, if you divide it in half until you got down to 1, the overhead of the mechanisms for fork join and the threading of fork join would dominate your work. So that never happens. Fork join never goes down to 1. No one ever does that. So we should realize that that matters. If you're always going to go down to n and not 1, then I don't think you want to imagine that you're going to go down to 1. If you go down to 1, you're stuck, right? How does filter have to work? It has to produce a result per everything, which you get into the goofiness that you see in his talk, where a filter is returning, you know, if it gets 42, it returns a list of 42, and if it's supposed to filter something out, it returns an empty list. What is that doing? That's just creating work for the next guy. Right? The next level of your parallel thing has got to go and remove all that stuff that you just made just so you could communicate to him that there was nothing to do. That doesn't make any sense to me. Right? If you're going to get to the bottom and you know you're going to have n left at the bottom, and if the best way at the top to apply a function to n things is reduce, guess what the best way at the bottom is? It's still reduce. So instead of map reduce, fold is reduce combine. And that means you have the opportunity to use distinct functions for these two jobs. So we'll look a little bit at fold. Like reduce, fold is built on a protocol, which means you can apply. It's going to try to ask the collection to do it first. If a collection cannot do it, it turns into reduce, because the semantics are actually the same, right? The potential parallelism is just a potential thing. Oops, you didn't get it. Okay, still warned. Right? So we ask the collection to do the work. We have a protocol. The basic idea is this. The collection is going to be segmented. Each segment is going to be processed with reduce. Right? And then the result of those segments are going to be combined, because you'll notice fold has another argument, right? Reduce was reduce with an initial value at this function, with this function, an initial value in the collection. Now we have fold, this combining function, reducing function, collection, and what's missing? Initial value. There's no initial value because it's not a monotonic process, right? Reduce is a monotonic process. That's the other side of being sequential. There's a seed, and that seed is manipulated one step at a time to produce the answer. If you have to take the seed out at the top, or you can't make a parallel. But it raises the question, right? What's going to happen at the bottom? We say we're going to reduce all these segments. What initial value is going to be used at the bottom? Right? Because the combining function is going to combine the results. So we're going to reduce the leaves with reduce. Where do the seeds come from? They're actually going to come from the combining function. If you think about it, that makes sense, right? You're reducing at the bottom. The results of the reductions are never passed to the reducing function. They're passed to the combining function. So the combining function really cares about that. Now there's a mutual relationship between the two, and sometimes it's the same function, right? If you want to fold with plus, the reducing function is plus, and what's the combining function? It's also plus. So in that case, you can leave the combining function out, and it's going to be the same as the reducing function. But if you were saying, I want to reduce with make a collection at the bottom, I want to merge with, I want to combine with merge the collections, those are two very different functions, right? Make a collection, merge a collection. And the problem with any design that uses fork join that says it's one function is it can't do that well. It cannot do that well. It can't do it with another step and a whole bunch of, monkey business in between it. Now we can, right? We say reduce with this, combine with that. And so there's a notion in fancy land, monoids, that have this concept of a monoid is a binary function that has a special value, and I'm going to say it has a set of values that have a special property, which is the identity property, that if you say, do this operation with an identity value and something else, the result is something else, and vice versa. So it's essentially a value that disappears, right? We have identity values, right? The identity value for plus is 0, and the one for times is 1. So we have those, and in fact, there's already a convention for that. The common list guys are like, they were thinking of everything so long ago. Because everybody looks at plus, they're like, why does plus with no arguments return 0? Why is plus with, times with no arguments, return 1? Because I was going to need it now. No, they were thinking about these things too. So there's a notion of an identity that has to be true for any kind of combiner. And what's going to happen is each of the sub-reductions is going to call the combining function with no arguments to supply the seed, because we need a bunch of seeds. And the combiner is going to need to combine those seeds, and sometimes the reduction is going to produce no results. So if it starts with the seed that the combiner provided it gives it back to the combiner should be happy with that, right? So everybody has the right role. Everybody has the right level of control. So this is cool. So how do we get to using it? Right? We want to use these guys. If only we could make them independent of order and collection type, we could make them foldable. Already did that, right? There's nothing associated with making these parallel, right? Map and filter. If they're given something that's foldable, right? So sequence isn't foldable. It doesn't know how to divide itself in half efficiently, right? But a vector is, and a map is, and anything that's tree-like is, right? As long as what they're being asked to work with is itself foldable, their result is foldable. So we end up with something, but there are some reducers that are not like that. Like take actually at its own level of logic cares about order, because it's supposed to count what it's doing. So take is not foldable, but map is, and filter is, and mapcat is, and a bunch of other ones are. So you see this thing folder now. It looks a lot like reducer, right? It's going to take a collection and a transformation function. The same ones, the exact same ones we were using before, not different. They have all the right properties, right? It's going to extend reducer, call reduce, like it did before. I just left that out. And it's now going to implement or extend call fold the same way. You're going to ask me to fold myself. I'm going to ask the collection to fold itself with the same combining function and a modified reducing function. I only have to change the reduction at the bottom. This is the other big bang from moving away from MapReduce, is that it allows the reducers framework to immediately be inherently parallel. So all these things are all tied together. By sucking everything out of map and filter, we ended up with something that you could drop right into the bottom of a fork join strategy, as long as that fork join strategy was based around reduce at the bottom. So there's a synergy here that really makes it work. So, in summary, the idea is you build map and filter and these other things as reducers. They're independent now of collection and order, so they're parallelizable. The beautiful thing about this is you don't end up with parallel this and parallel that. There's not parallel map and parallel whatever. There's not parallel vectors and parallel arrays. And what is a parallel array? How can you tell if you're looking at two arrays, which one is parallel and which one isn't? It's just silly, right? That makes no sense. That's just object-oriented, like, brain destruction. It makes no sense. Parallelism is an attribute of an algorithm, not a data structure. Right? So we don't have any of those things. And I think this is an example of simplicity in practice. Right? We've now separated these things completely orthogonally. Folding, the notion of a collection, navigation of the collection, reduction, and the essential nature of the job to do are all in pieces, which lets us build these cool little things. And now let's see. Wow, this is really scary. Make sure we're all seeing the same thing now. All right. Let's do this. Start from scratch. Okay, so we're going to require, everybody good? Can see this okay? I'll make the bottom bigger. So we'll require the reducers. And the points made in the prior talk are sound, right? This does not replace lazy seeks. They are completely complementary. They're for two different kinds of jobs. Lazy seeks are still going to have a lot of value. Things that don't fit in memory, side effects, the caching properties, not realizing everything. There's a whole bunch of benefits there, infinite sources. They're complementary. They're strictly complementary. So we can have both. So we make a big vector here. And you can't really see where my cursor is because I don't know how to change it. So now we're just going to do, I'm on the third line. I'm just going to do the ordinary lazy seek calls. Filtering the even numbers out of this vector, then mapping ink across that, and reducing with plus. And that's once. I'm going to call this a couple of times and let it warm up because the first guy's going to get penalized. And there we go. That's where we're at. Now we're going to just switch here. We're going to switch to the reducers map and the reducers filter. This is the same old reduce. It's the same vector. Right? This is Legos. We just plug in these two guys. And we swap that out, and boom. Look at that. And now, same thing, except instead of asking it to reduce, I'm going to ask it to fold. I should get the same answer, right? Folding is really, especially with the same, I'm not doing a complex fold that uses a different kind of combiner. Folding with only a reducer should produce the same answer as reduce. It's just an optimization. But what an optimization. Look at that. That's it. So, any questions? Yes? How distribution could be introduced into I don't know. I lost enough sleep about this and I can't start thinking about that. But, so in principle, you're already starting on a good path, right? Because you have all this isolation from the facts, which is how you get to move something into a different context. Yes?
Maybe you should be questioned, how do you arrive at the size of the smallest chunk of the workflow?
That's a great question. So the question is, how do you decide what the smallest chunk should be? Right? How do I derive it? I don't derive it. That is extremely dangerous to do. Right? And all the fork join stuff you'll see is going to say, oh, it's going to have this lingering question. This is an important thing, right? If you have a really small job, how big do you want your segments at the bottom to be? Big, right? If you have a big job, right, each item is going to take a long time. How big do you want the guys at the bottom to be? The leaves. Small. How can I decide that for you? Have I decided it for you? In fact, I haven't decided it for you. Fold in its full form takes a partitioning size, then the combining function, then the reducing function, then the stuff to reduce. Yeah, that's enough. So it's an optional argument. I've left it out in all of these, but it's there. It's set at like 512 right now, which is fast enough to make plus faster, right? Which is good. And there's not tremendous benefits for making it bigger than that for very, very tiny work. But if you have bigger jobs, you can go and play with that, and then you will have to tune for your application. You'll have to try it, but you can come up with a number and supply it, and you're not tied by some defaults or waiting for me to come up with some magic estimation strategy, which is, the Fortress people are trying to do without it. And it's very difficult because they have to tackle that problem, which is really a research level problem. How can I estimate the cost of your work so I can pick the right partitioning size? That's too hard for me. So I let you pick it. Yes? A fork join map that works like the regular map? That's lazy? Fork join range is definitely going to be possible. We're going to have a foldable range. We're just deciding how to do it. Does that answer your question? Okay, I'm not sure. Yes? Yes? Yes, correct. Did everybody hear that? So there's two ways to compose them, one with the reducibles and one with the reducing functions. The reducing functions would be like saying comp, R map, R filter, right? But the thing is, one of those is going to have to be partially bound, right, in order to get the collection in there, right? If you want to compose the reducers themselves, you could say comp, R map, inc, R filter even. Now you get a reducer out of that. It has not yet been associated with a collection. And the nice thing about that is that's something that you can then pass to somebody. Here's the recipe for pie. I got no apples. But when you find some, this is how you do it.